cryptography in real world and cryptography in CTF isn't something that you should hate. It isn't something that you should be afraid of, and that's what we're here today to try and dig into. But we're only going to spend time on one type of cryptography, which is RSA. And thanks to Max and the crew from down under CTF for putting that CTF on, because it is fantastic. So we will attempt to show some practical examples of how you break certain cryptos and succeed at CTF doing that. And who am I? I'm Kris. I work at Google, but I've been CTFing for about 7 years, and I can remember the first CTF I did too. And I also, as Max did, credit CTFing to some professional success. I also credit CTFing to some of my early success in my Google career, specifically. I don't think I probably would have got this job if I didn't CTF a lot. And my love for contributing to open source projects was kind of founded in CTFing as well, because there's so many tools out there, so many things you can contribute to that make other people's lives better when they're working on CTF. So it's a really well-rounded type of security-specific thing to do, and other professions have this as well, like mathematics has mathematics championships, and software engineering has software engineering championships too. The security one probably has the lowest bar of entry to be successful in, so I think that's pretty cool. So, as we learned in the previous talk, CTFs have two different formats, attack and defense, and Jeopardy. Jeopardy style is the most popular, and this is kind of what it looks like, right? You have a series of challenges available within categories at various point values, and you can choose to do them, and you can succeed at them. And in this case, this person was really successful. They did heaps and heaps of challenges. And can I get a show of hands who have experienced this kind of CTF before? I just want to kind of get numbers. Yeah, we've got definitely some people in the crowd that have CTF'd and Jeopardy CTF before. That's great. And here the green ones are done, and the ones that are white boxes still are undone. It's a pretty good effort by this team, and they did almost every challenge except when I revealed the other category of challenges, which they didn't even attempt. That's why I'm motivated to give this talk and try and motivate some of you into overcoming whatever it is that is making you skip crypto challenges or making you not even attempt crypto challenges, which we'll find a little bit more about. This happens a lot. So for me, this talk starts back in 2015 when I worked for a different company. I was encouraged to join their company-wide CTF, and kind of was a little bit peer pressured into it, to be honest. I wasn't really interested, but I got into it, and turned out to be really, really fun. Great team of colleagues that I played with, and we ended up coming first on the qualifications, so I was like pretty stoked. I had some success, but not only that, we got to go to the finals in the US, which was super fun. They set up an entire fake hospital with fake patients and fake monitoring equipment, fake like ECG machines that we had to, and various scenarios around those machines that we had to break into them, and like it was so fun to do that. They set up a fake pharmacy with fake point of sales terminals, and we had to hack all of that and we had to kill patients, and we had to give them wrong doses of medication, and it's pretty scary, but okay, that's real life. That's what hospitals are like if you go there. To get points in the CTF, by the way, they gave you a real world open source medical records, like CMR database tool, and you had to find 0 day in it. We found like 6 0 days per team. So that's how disappointing the software was. But up until that point, when I'd started doing that, had made so many assumptions about CTFs that they were too hard, they were not for everyday people, they were just for like absolute geniuses. I definitely couldn't take part in them. I couldn't win them. I couldn't. It would be so hard that I wouldn't just not succeed. I would embarrass myself. Or worse. So when I had fun at that CTF, I'm like, wow, maybe this is for me. So I decided to give it a shot in the wide world. I looked at all sorts of challenges, but when I got to the crypto challenges, I would just skip them. They were another level for me, and But if you think about it, it's just another version of the same fear I had going into CTFs in the first place, right? So it's like this kind of imposter syndrome. Competing in CTFs was not for me. I wasn't smart enough. I wasn't good enough. So this like cryptography thing is just another level of the same problem. I wasn't into math. I didn't know anything about crypto. I can't possibly solve them. But one of the first things I did do when I got into CTFs was promise myself that I'd use them as a learning opportunity. So I would try and teach myself through doing the challenge, learning along the way, and then like reinforcing that teaching by doing write-ups. So has anyone written a write-up in a CTF before? If you do CTF challenges and don't do write-ups, I urge you to give it a try. Even if you don't share it widely, just put it on your own GitHub. I post mine to CTF time, but you don't have to. It helps reinforce the stuff you might have learned. So I did that. I registered a domain name, ctf.rip, if you want to know where my website is. And I started doing write-ups. I did really well in B-Sides Canberra 2016. CTF, I came third, soloing, where I think the winning team was like Cybears from ASD. They're really good. And I can't remember who came second. Sorry if you're here. I just published as much as I could. This didn't help me a lot, though, with the distinct like crypto. And so over time, I started getting really like concerned that I was never going to ever do a crypto challenge. So I decided to embrace my naivety one day and just give it a try. But so there was a Chinese CTF called CTF in 2015. They started the CTF with no challenges available to play. And then like people started complaining, and then they finally opened one challenge, and it was a crypto challenge, and everyone started complaining again because they didn't want to do crypto. But it was a warm-up challenge, and warm-up challenges in CTFs means they should be easy, right? And so I opened it. It was an RSA challenge, which is, we'll talk about RSA and what that is in a minute, but within 15 minutes of Googling, like, or maybe 5 minutes, like, or maybe a couple of seconds, I can't remember, but it was done. It was finished, and I could move on to the next thing. And like, you're like, wow, that's easy. Like, everyone should be able to do that. But actually, if you look at how many solves it got 86 solves. And if you look at how many people solved the check-in challenge, which is where you just say, I am here, and you basically copy-paste a flag from Discord into the flag thing. 567 teams did that. Only 15% of the people went from copy-pasting to Googling for 5 minutes, which is just says a lot for how much people do really hate crypto challenges and CTFs. And I've come to learn this weekend, actually, that this could be connected to a phenomenon called learned helplessness, where players who have repeatedly struggled with stressful challenges like cryptography challenges, perhaps, may have conditioned themselves to be entirely avoidant of them going forward. And so they're just leaving all these points on the table. And that's kind of where I'm going with this. So it's kind of, I had this imposter syndrome. Lots of people have this imposter syndrome. Max is probably suffering from imposter syndrome because I bet he'd do great if he just tried crypto. He probably does anyway, but we'll see. And it sparked my interest to solve more and more of these. So let's get down to the nuts and bolts. What is RSA? It's a cryptography algorithm, right? It's an asymmetric cryptography algorithm, which means we sometimes call it public key cryptography. The idea is that we actually have two keys that are participating in this crypto system, right? So we have something called a public key, which we can, we generate. It's related to the private key, but we can freely share it with our friends that we want to communicate with within certain, boundaries of sanity. But we don't talk about those. We'll just say that for now, sharing your public key is fine. You can share it openly, but you must keep your private key secret. And it should be computationally infeasible to recover the private key from the public key. That's really, really important. It gets its name from the initials of the author of the original paper in 1977, who were Revest, Shamir, and Edelman. It's based on the principle that finding the factors, that is the divisors of really large numbers, is computationally very difficult. It's a very hard problem. And it's one of the most important crypto systems and cryptographic algorithms in the world to even today. And it's very commonly used as a protocol to do key exchange for other algorithms like symmetric algorithms. We use it in lots of things like TLS, which secures the internet today. And it's popular for CTF challenges because there's so many things that can go wrong. And that's where CTF challenges, they live in that little niche area of things that go wrong. And so what are our goals when we're doing CTF challenges that feature RSA? So helpful might be to get the message, the plain text message that the cryptography is protecting in the first place, and that's kind of usually the goal. Usually the plain text message is the flag, right? So it's pretty simple to like get through from A to B and go, okay, that's what I'm looking for, the decrypted plain text. But it might also be the challenge to just get the private key. If we can get the private key, it's kind of even better than having the plain text, because we can decrypt any ciphertext that we have now and any future ciphertext encrypted with that key as well. We can also sign messages, which also comes up in CTF sometimes. I'm going to do a little bit of a speed run through the math. Actually, I cut out a lot of the math because it's not actually that interesting, and it's also not that necessary to know to be able to solve RSAs. And it sounds weird, right? I should know math to solve math things, but you don't really need to. It's just as long as you know what the algorithm looks like. And up here I've got it. The encryption algorithm is C equals the M to the E mod N, whereas the decryption algorithm is M equals C to the D mod N. And what are these things, right? Let's talk about what the letters mean, because that's the important thing, so that you can recognize what RSA is, and then so you can operate within the challenge. So we have M, which is some message that we want to encrypt, some plain text message. It's usually the flag in the case of a CTF challenge, or at least some message that contains the flag. Could be quite a bit longer than just the flag, and it's important sometimes that it is longer than just the flag. C is the ciphertext / the encrypted version of the flag, and it's the result of doing the encryption operation. We have a modulus, N, and we have two exponents, E and D. The E being the public exponent, and D being the private exponent. And going back one to the modulus is the product of two prime numbers, two large prime numbers. So a prime number is any number that's only divisible by itself and the number 1. And there are special numbers that are important in math, and they're important in cryptography. And if you have sufficiently large numbers of them, if you have sufficiently large prime numbers and multiply them together, the resultant composite number is extremely difficult to get back the prime numbers that you put into it in the first place. And that's the foundational principle of RSA, is that prime numbers, once you multiply them together, it's very, very hard to figure out what those two numbers were in the first place. It's probably important to also mention that you don't just have to have two prime numbers in RSA, you can have any number of prime numbers, but there's diminishing returns of the security properties of RSA as we add more and more prime numbers. So for the most part, you'll see two prime numbers used in RSA, but you can see any number of them actually. And once they go past P and Q, we call them R1, R2, R3. There's some math about how we derive the private exponent, but I won't go into it. You can do your own research there, but it's almost never necessary to super know that unless you do certain categories of challenge, which I'm not going into today. But it's definitely a good learning experience to go through that. Because we're going to use tools a lot. We don't need to know everything about RSA math because there's a fantastic array of tools out there. And that's kind of where I'm going with this talk, is that you might think that this is such a great gift to be surrounded by. You might think that you have to know a lot of math and you have to go through a lot of steps to do RSA, but actually there are such great tools out there now that it's a lot of the time it's just pattern matching what the problem is and using the appropriate tool to solve. Or sometimes there's multi-steps before you get to the point where you can use the tool, but it's important to know what the tools are so you can know what's out there. And the tools themselves will give you a lot of hints, and sometimes they even have automatic solution modes. Let's talk about a little bit what they are. So Python is not really a tool, it's a programming language, but has a great crypto library called PyCryptodome, which is the successor to another library called PyCrypto, but PyCrypto is long dead now, I think, and PyCryptodome replaces it, and you can just pip install it. Sage Math, it's an open source language for math, and while it's tricky to learn and it's kind of tricky to use, mathematicians thrive in it because it's very easy to use if you know the math from the beginning. If you don't know any of the math, then using it is a little bit hard. It's useful because a lot of the open source tools that are published to solve certain RSA challenges are written in Sage. It's a derivative of Python though, so you can still read them if you know Python, but Sage is pretty neat to know about. And install, it's 1.5 gigs to install. You never want to install it on the fly in a CTF, it takes forever. So install it now. RSA CTF tool is a Python tool written by Ganapathy, a guy from a famous CTF team I can't remember the name of now, but he made this tool years ago, and when I found out about it, I was like, wow, this is an amazing tool. I contributed a lot of code to that, and then over time it got better and better and better, and now it's probably the best tool out there. Notwithstanding Go RSA tool, which I wrote as a project to get better at Golang. Like, hands up if you've ever written a tool just to get better at a language, even if you didn't care about the tool itself. That's why I started that. I didn't really care about having a tool, but now it's like massive. It supports some of the most weird RSA edge cases, and yeah, we're going to use that in this talk, so I don't need to talk about it too much more. All right, so what does RSA even look like in the wild, and like what does a vulnerability in RSA look like? So it's it's not obvious really. We're going to go through a few patterns of what it's going to look like, but you do need to have some prerequisite knowledge, but this is kind of prerequisite knowledge for all CTFs anyway. So base 64 encoding, it's just a way of encoding any binary data using an alphabet of 64 characters. Most people in any CTF situation will be familiar with it because it's kind of like a staple of CTFs. Like the first crypto challenge in most like entry-level CTFs will be just a base 64 encoded flag, and they'll expect you to sort of like use pattern recognition with your eyes to recognize it, put it into CyberChef, which is a really, really fantastic tool made by CSECcon, and decode it, and that's your flag. And so once you're used to recognizing what base 64 looks like, it's a really useful skill. And then we're going to see keys, RSA components, like those D, E, N, P, Q, C, M things that I told you before, those letters. They're going to be encoded in numbers as well. So decimal encoded, so just large decimal integers, or hexadecimal encoded large integers. So don't be sort of discouraged when it doesn't look like a number at first sight. Maybe it looks like bytes, like a hex string or a base 64. Could just be a number hiding in there. And this is what RSA public key looks like. In fact, all RSA keys, when they're correctly ASCII armored, will look like this, but this is a public key. It's called PEM format. It's not important to know that. And it's the most common format key you will see in the real world. So like a lot of certificates will look like this, and they'll contain RSA keys as well. It's base 64 data. So the thing between the begin RSA public key and end RSA public key is just base 64 version of a binary version of that key. And sometimes you'll see keys encoded in, like I said, numbers. And here I've got like a JSON format one, which is just the number N and the number E. So N being the modulus and E being the public exponent. Together, those two things represent an entire public key. The exact same thing here is represented here as just two numbers. They're actually the same. They're equal in terms of like how you solve the problem using them. And then we've got like another version of a key here. We've got N and an E and a C. N being the, again, modulus, E being the exponent, and C being some ciphertext that someone's encoded with this flag, encoded with this key. And in this case, the ciphertext is probably the flag, right? So our job is to use these numbers to get a flag or some other plain text. So let's talk about vulnerability one. We'll go through a couple. We won't go through that many because we don't have enough time to go through as many as I want. But this one's called well-known factors. So remember before when I said the property of the modulus is that it's a composite of two large prime numbers? If you have ever seen that composite, that modulus before, there's a chance that someone else saw it and they've documented the factors. And there's a cool website called FactorDB. I don't know, it's cool to me. It might not be cool to everybody. FactorDB, and it contains tons of factors of large composites, because actually like this whole prime number thing and finding factors of large composites is actually a hobby for a lot of people. And there's competitions and like worldwide competitions about cracking large composites and things like that. So this is interesting to some people, and they've documented it for us, so we can use that. And the tools will go out and they'll look for this FF which means fully factored, and if it's fully factored, then we know the answer. So we can firstly hit the first problem. We've got this like thing in yellow which looks like an RSA public key that's encoded in base 64, but we just want the numbers because we just want to see if this n is factored online. How do I take the number from there and put it into the website? The tools do that for you. And here, like, I'm using the tool that I wrote to get the key components out and just dump them to like your standard output so that you can just copy paste it. You don't have to do that though, because the tool will also go to FactorDB for you and use the API to check. So that's a pretty cool vulnerability. You should try that first, because even when it's not the intended solution, some like teams that solve challenges early will accidentally submit their factors to factordb.com, and you might just snag a free prize. Which leads me to another vulnerability in RSA, which is just having small factors, small prime factors. So this is hypothetically, you've got this key that looks really long, the number n is really, really big, the key is really, really large. I mean, you can still get a valid RSA key if one of your primes is really small. Like, what if it's like 7 or 11 and the other prime is massive? It still might look like a legitimate key, but you might be able to factor it really quickly. And so what we can do is we just try and see if we can factor it. There's a bunch of tools that will try this for you, and this is guaranteed to work extremely quickly up to a modular size of 256 bits, but it might work for larger ones too if one of the primes was small in the beginning. So we said before that n equals p times n. If n equals p times q. If either p or q are small, then you will recover them very quickly. And so here we've got this tool called Yahoo, which is a pretty cool tool that, in this case, factored this key in like 67 seconds. And that's a 256-bit key. You would think it's a lot, but that's like a minute's worth of factoring on a regular computer. So pretty easy to do, pretty quick to try. I spend 5 minutes on attempting to factor keys if I'm unsure about what other method I would use, just to see if it's like a small prime problem. So not really easy to spot, but you can, like I said in this slide, check the bit length of the modulus, and if it's 256 or lower, just give it a try. You'll get it in a minute. We have, we're moving on away from simple attacks to things that rely on people using it incorrectly, or generating keys incorrectly, more accurately in RSA. In this case, we have two different public keys which encrypted a message, and what we're really interested in doing is finding the private key. Turns out that when these two keys were generated, they shared one of the primes only. So you can see here that there are two different numbers, public key 1 and public key 2. Glad we have so many screens so people actually see this. But these are different numbers, but actually they shared one prime during calculation. You can use something called the Euclidean algorithm, which is a really efficient way to find the greatest common divisor between two numbers, and you can instantaneously recover that prime that was shared between the two of them. It's pretty sweet. And now we've recovered one prime. We've actually broken both of these public keys into their private keys, because we can just take the Q from each one of the divisions. And this is sounds like a pretty hypothetical attack. Surely this doesn't happen in the real world, but no, it does. It happens in the real world. And in 2012, I didn't, but somebody did a research into widespread weak keys on the internet, and found that a lot of the SSL keys that were in use at the time shared common primes, and found hundreds of thousands of instances of broken SSL certificates around the world, live on the internet. And then in a further study, they found that lots and lots of like consumer level IoT devices and things like that were generating really, really weak key material. So therefore, like, were trivially able to be cracked as well. So, you know, it's not 2012 anymore. This was 10 years ago, but I do think that there's still this kind of problem prevalent on the internet today, although I haven't seen any published recent research Which brings us to another attack type, common modulus attack. And this is when you take two of the same public keys, two keys that share the same modulus. They're not the same public key though, because they have a different exponent. In the left-hand side, I have an exponent, public exponent of 3, and on the right-hand side, I have a public exponent of 65,537. Both public exponents are considered safe, although e equals 3 is not really considered to be safe in many situations anymore, but e equals 65537 is definitely safe. Given these two keys and these two very different ciphertexts, we're able to recover the plain text in like 0.0 seconds. So very interesting attack that I won't talk about the math, but it just works because of math. But you can see that the tools here are doing the work for you. You just need to use pattern recognition to notice that these keys are the same, but they have a different modulus. The keys are the same because they have the same modulus, but they have different exponents. Once you've recognized that, you've done pattern recognition with your eyes, you can go straight to the tool and get the answer and get the flag. Small public exponent attacks. Actually, this is another one where you have, where you show that the exponent of 3 is not really secure. And in this case, if m to the e is less than n, then m equals the eth root of c, basically. So you can trivially find the plain text from the ciphertext just using some quick math. I'm running short on time, so what I might do is skip this attack, but you can read it in my slides later. I'll share them. And talk about large public exponent attacks, which are really interesting. Here we have a large modulus, really, it's like 4,096 bits or something, and then we have a really large public exponent, which is super large. Again, pattern match with your eyes, you can see this E is abnormal. We're used to seeing E's that are like 65537, right? As soon as we see this E, we go, that's interesting. It turns out that we used to do this because calculating the private exponent, if it's really small, is really fast. And when we had not much compute power on the internet and we wanted to decrypt SSL, we just make huge public exponents and have really small private exponents, which was a benefit, but it turns out it's trivial to crack those and recover the key, the private key from that kind of situation. So we don't do that anymore. We have some more different types of pattern match with your eye situations here. And in this case, we have a defective exponent. In this case, we have an E of 100. Now, what we've seen so far are E of 3, E of 65537. We've even seen this really huge E. We haven't seen an E that's been even, and there's a good reason for that. E needs to be co-prime with the private exponent, but this is like an even number. It really doesn't work. RSA doesn't work this way. If you don't have an E that satisfies certain parameters, like it must be prime for a start, it will start to, this ciphertext will start being able to resolve to multiple plaintexts. So you'll never really be able to know if your decryption is correct or not. So what we can do is we can just use what I call a crib, which is when you know some of the plaintext. In this case, it's a CTF challenge. You know the plaintext is going to start with a flag format. You can use that crib to brute force all of the possible plaintexts out of that ciphertext and eventually arrive at the correct one because it starts with the flag format, right? So that is also covered by tools. And again, another example of how to use pattern recognition with your eyes to come to a really quick solution, which is kind of where I'm going. With this primes too close together, I'll really spin straight through this one. If you have a P and Q that are really near each other, you can trivially find them using Fermat factorization, as well as Karl Londal's close prime factor. There's a bunch of algorithms, but it's not that important. You can just tell the tool to do them. There's so many more. I could talk about them for probably another day. But they're all covered by tools, right? RSA and JWTs is very interesting, and OAuth2 also does the same thing. They present key material that they don't expect you to have, but you can recover it. If you have 2 JWTs, you can use an attack to recover the key material. Only the public key, but then if it's a weak public key, you can go and try and recover the private key. You can recover the private key from when you have a partial leak of the material. Not even half of the bits are required to do that. There's RSA Oracle attacks where you can ask a server. Anyway, there's a lot of stuff. It's all fun. A lot of that's implemented in tools, and some of it's not. So if you're interested in contributing, that's cool. And more. It could go on, but I am out of time. So wrap up and takeaways. Okay, so crypto isn't actually that mysterious, and a lot of the solutions can be had from just like using your eyes to come up with pattern matched sort of ideas on how it might be solved, and then you can use a tool to like confirm your solution. Usually the tools will crack these things in seconds rather than minutes, because that's kind of the math of it. The math of doing things wrong in RSA usually means it's totally broken immediately, not so much like you need like extra time to crack it. And if you do need time to crack something in RSA, it's usually in the order of 3 or 5 minutes, not hours and hours and hours. It's possible to dabble as an amateur, and it's even possible to like give back to the tooling as an amateur, because the tooling is in a pretty good state, but it could always be better. Crypto is really satisfying to solve, because you're going to solve a bunch of challenges that no one else has solved because no one wants to do it. You know, I obviously don't support that. You shouldn't try crypto. I think you should try crypto, but because of the global shortage in crypto willing participants, it turns out that you will solve a lot of challenges that nobody else is solving. And it is possible to burn out when you repeatedly struggle, but it's equally possible to become motivated, again, once you've heard about the phenomenon of kind of learned helplessness that we talked about a little bit earlier. And despite the weaknesses in the way that people have implemented RSA, we've done a lot well, I haven't done anything, but some people have done a lot in making it harder and harder to break, and still really important to this world until, I guess, quantum computing can trivially factor large numbers, which is maybe a possibility in some time in the future. It's going to be important until then. And that's it. Thanks, Alex, for suggesting some things for this talk. And that's it. Thanks, everyone.